Okay, so we've talked about enantiomers, right? So we got to the point where we're starting to talk about two centers. What happens when we have two centers? How does that change? Can you guys see the screens?
Yeah.
Okay. Yeah. So in the case of where we have two asymmetric centers, then we have the ability of having, in some cases, 4 enantiomers. All right. You guys take a look here. So here's one enantiomer. Here's another enantiomer, 2 sets. Right. So 1 and 3 are enantiomers of each other, and 3 or 4 are enantiomers of each other. You guys remember these are Fisher projections compared to the Newman projections. You guys remember the Newman? Okay, can you guys see the distinction between them? The two enantiomers. Okay. Okay, so this is just basically saying what we just said. So we talked about diastereomers. So where 1 and 3 are diastereomers of each other, but they're not enantiomers of each other. Right? You guys see that as well. So like these guys are on the same side where these guys are opposites of each other. So diastereomers yes, they are going to have polarity differences, major polarity differences. So even though, so these guys are enantiomers of each other, and the polarities are always going to be opposite of each other, right? That's going in one direction, and R is going to go in the other direction. That's the same thing with these guys. Well, these guys are going to have a different polarity as a direct result of that. Like of these guys, let's say from here to here, comparing the two. Okay, so these guys actually have different chemical properties and physical properties. So point out. So 1 and 3 are going to be different in chemical properties and physical properties. And that's because the location of, let's say, the chlorine and the hydroxide, in this case, they're opposites of each other, right? Where here, they're all both the same. Even though these guys are going to have the same property. Okay, 3 and 4. Okay. You guys with me so far? Haven't lost you yet? True? Okay, so you guys actually, I think I had you guys build these the last time, right? Okay, so you guys are familiar what they look like and how they behave or how they're going to look a little bit different, right? Okay, so here, these guys are enantiomers of each other. And so these guys are going to be cis, these guys are going to be trans. These two are enantiomers of each other. Okay, so here, the first thing that we always want to do is try to identify our asymmetric center, right? And then, so the 4 groups, so in this case, we have this guy, that's one side, here's 2, here's 3, right? So we have to use this whole array to sit there and distinguish between the two. And so we can see clearly how these are different from each other, because one, again, is cis and one is trans, right? So, but we can also see how the enantiomers are different from each other because they don't sit right on top of each other. They're not transposable. Okay, so then how would I distinguish between these two? So we would use, okay, so we need to figure out which one is going clockwise and which is going counterclockwise, but we have two centers. Right? Don't we have two centers? I have a mistake. Okay, so then we'd have to look at both centers, right? So we would count our carbons, right? And so if this guy is considered 1, that's going to be our first carbon for the bromo. This is going to be the third carbon. So then we're going to sit there and say whether 1 is R or 1 is S. So is 1 R or is 1 S? So let's see, we have, this is 1, 2, 3. So looking at our attachments, we have 3 attachments. We have 1, 2, 3 attachments, plus technically our, this is right, 1, 2, 3, 4, and now hydrogen here, right? So these guys are in the same plane. We have this one coming forward, and then that means that this guy is going to be in the back, the hydrogen. So how will we count that? Is that an R or is that an S? So I should draw it as a wedge, and then a dash towards the back. I know I messed up dash. Okay. And how did you get S? So where's 1? Who has the highest priority? Okay. Then this carbon or this carbon? The bottom. Okay, so this is 2. And then this guy would be 3. And then the H would be 4. So if we look at this, it would just be, if I remember correctly, that's counterclockwise. True? Or do you guys agree? Disagree? So in this case, the hydrogen is dashed because the bromo is facing us. Yeah. Okay, so then we have, it'll be 1s. Oops. So this guy would be 1s. And then what about the 1, 2, 3? The 3 carbon? Who has priority? Again, it would have a hydrogen going in the back. So 1 would be, would it be this one? Would it be this one? Or would it be that one? What was that? The CH3. So that's going to be your 1. This guy's going to be 2. This guy's going to be. So this guy is going. Is that going clockwise? So then that would be 3s. I mean 3r. 3r. So this guy would be 1s 3r cis bromo cis 1 bromo 3 methyl cyclohexane. Are you guys with me? You have a look. Yes. Yes. Hydrogen is always going to be lower. Yes. Yes. Because the bromide is right. Yes. So it's, and then you have the methyl groups, and also in terms of priority, the bromide has, although they're all considered about the same when we do nomenclature, right? And they get bromo, they get put up in the front, but they have priority over the carbon chain. So this one makes it a little more difficult because we have a methane here, methane, and then we have the chain itself. So then that becomes second priority because it's part of that chain. No, you just location. You'd put it in terms of location. So then it would go 1s, 2, or wherever it's located. You want to put it in terms of numerical location. Does that make sense? Okay. And so we could do the same thing over here, right? And that guy, in theory, should be opposite, right? Because that's how we determine our enantiomers. They should be opposite of each other. You sure? Okay. So, and then we could do the same thing over here with the trans. You guys feeling it? You with me? Nobody's ready to jump out of a window yet? You're not allowed, even if you want to. So, no jumping out windows. I know organic chemistry. I told you it's a lot of memorization. Remember these little details. It seemed like, right? Okay. So in this case, this guy doesn't have any enantiomers, right? It just has cis and trans. Okay. And there's no asymmetric centers, right? Because we got the same thing on both sides, right? I'm gonna think. I think it could work on hexanes as well. There's one on top and one on the bottom. It's just location where it's at. It's located at. Because let's put this guy down in the center right there. We're good to go, right? Same thing. And then if it with the hexane, it's the same concept. It's yeah, hexane. So if I had okay. Well, it's not the best split, but you kind of get the idea, right? Oh, speaking of that, there we go. So you asked the right question. Okay. So again, no asymmetric center. So then that way we're able to sit there and just use two stereoisomers. Okay. So you're probably going to get on a test on that. It's like, how many isomers can you get from the structure? Blah, blah, blah. Right. And then I'll give you this name here, and then you're going to have to tell me. What was that? 2 to the n. Well, but in this case, you only have 2 stereoisomers, right? So that does that hold up? We have 2 chiral structures. Yeah, was that? Oh yeah, yeah, that's right. It would be to the end, yeah. So it would be based upon the number of where n represents the number of centers that you have. That's right. Okay. So okay, so here we have 2,3 dibromo butane. Well, 2,3 dibromo butane actually has 3 stereoisomers. It has a Meso compound and it has 2 enantiomers, or a pair of enantiomers. Okay, so here are our enantiomers. And then here's our mesium. Okay, enantiomers. This is the same structure, but shown in Fisher projections rather than, okay. And then this is our, hold on, lying to you. This is actually drawn wrong. Because this is coming out, this is coming out, this is coming out, this is coming out. So this is trans. They actually, this is drawn wrong. So there should be one going in front, there should be one going back. So this is actually drawn wrong. So these guys are trans to each other. These guys should be trans to each other. Does that make sense? 2 and 3, yeah. So 2 and 3, these are supposedly the same thing. But the way that they draw this, both of those are coming out towards us. The bromines, if you take a look at the bromines, they're both coming out towards us. Okay, so those are both cis. So they're the same structure. Essentially, they just screwed up on the drawings. This drawing is wrong. You guys, you see that? Where here they're trans to each other, right? So that means one is coming out towards us and one is in the back. Can you guys see that? Yes, that one is mess. Yes. So it's being compared to 2 and 3. These are not the same of each other. Diastereomers means that you have, so meso means that you only have one of them. The diastereomers means that you have, okay, these two match up with each other. So you have, okay, so diastereomers, you have 4 total, right? 2 in, let's go back. It's easier to see. Make sure I'm explaining this to you the correct way. Okay, so here, these guys are diastereomers of each other. 1 and, so these two are diastereomers of each other, right? And then these two are also diastereomers of each other, right? So meso basically means that you have only one of your diastereomers. You have not that, you have 2 enantiomers and one that's this just exists, right? Diastereomers means that you have di meaning 2 of 2, right? Do you see? Di. Let me go back. Come on. So di meaning 2. Okay. 2 that are not, 2 not stereoisomers, right? So these guys are not, you know, there. Well, they are, but not. Okay. Diastereomers. Okay. Where meso means that you only have that one. So we have the 2 that are enantiomers. And then this guy, it only exists because it's exactly the same. If we put the bromines on the other side, all we've done is just, it rotates and it'll be exactly the same structure. Does that make sense? Flip it around. Okay. Are you guys with me? Okay, good. Just making sure I haven't lost you yet.
Oh, this
Okay.
is tough.
Yeah, it's because they're the little, I mean, if you don't pay attention, there are little things that makes them different, right? Very little things where these guys are located. And if you flip them, how they behave, right? So if I flip this guy's going to look exactly like it does already, right? But they're never going to be exactly alike. Okay, where these guys, if I flip it, it's going to be exactly the same compound, right? If I put my bromine on the other side, I flip it, I get the exact same compound. Does that make sense? Okay. do me a favor. Best way of doing this is, let's do the 2. Let's actually do all 3 of those. Can you guys, you have your kits? Because that the best way of seeing it is seeing it. You know, I could sit here and talk until I'm blue in the face. Until you put it together, it don't mean anything. Let me guess, you didn't bring your kit. I should just start selling some Mesa. Make you guys keep them here anyway, huh? You don't use them at home, do you? Your building kits? I mean, your structures. You know what? I think I may. One day we're gonna have a part 2 to one of your exams and have you guys build structures using your kits.
I think one problem with my kit is like there's only 2 bromine in it.
There's only 2 bromine. You can use any of the halides, which are the green structures. There should be more than that in your green. Shouldn't there be more than 2 greens, right?
Yeah.
Okay, good. Yeah, because the green represents halides, if I remember correctly. I'm old and all. You guys are making Zach feel really happy that he bought this, that it's not going in vain. And he said he's going to have books for you hopefully next semester. Yeah. For the class. And then also the organic study guide. So we're not pirating. Well, technically we're not. We bought the damn book. You know, we bought like 4 copies of it. Can you use some of the chemicals for your altar? Yes, you can. You just need to let me know what chemicals that you're planning on using and what you're planning on doing with them, so that I make sure that it's not too crazy. And well, speaking of that, how you guys are doing that? Yeah.
There's number 1 on table 1 and then the one in the bottom of table 1. Are they
No,
no?
that's what I was saying, that they're
Okay.
screwed up, right? Because yeah, that's right. So I'll tell you which one is wrong. Let me see. So this is the 2 structures. These are the 3 that you should have, right? Because this guy is exactly the same. Let me make sure I'm not lying here. With these guys on top of each other, and if I rotate it, this guy is going to be, the BR is going to be up here, the other one's going to be down here. Okay, so these guys will never be exactly the same thing. For this guy, if I rotate it, it's going to be exactly the same thing, right? So they made a mistake up here, right?
Yeah, so
Exactly. They're going to be superimposable each other. If I rotate this guy. That's right. Even though they said these are technically mirrors, but these guys are also superimposable because I can rotate it to make it. You understand? So
we can have like mirror like enantiomers that are
no, if they're superimposable, they're the same thing. You understand?
oh, okay.
Does that make sense?
So
They're not isomers of each other, right? Isomer means, the general term means the same chemical formula but different chemical structure, right? So that's, and then we could break it down. Is it constitutional, meaning that we have a double bond and a single bond in this case, or, you know, or it can be or it's a stereo, right? Stereo meaning that it's just they're the same chemical, almost the same chemical structure, but they're not the same. They're not superimposed. Okay. So these guys are not isomers. Yeah, these are not isomers. They screwed up. The isomer should have been the trans. They should have had 2 trans like down here, right? So that number 1 is really number 2 here. This here, this is really number 1. 1 and 2 are really number 1. You see that? Because if I turn this guy and I put my bromine here, then my other one is going to go over here. It's going to be exactly the same. That's why I wanted you guys to sit there and do it. So you should be doing it down here, like this one. Yeah, don't do it like that one. Yeah. Okay, do you have all three of yours? No, but they're different. So, and so if you can do 2 or 3, the ones at the bottom, not the ones at the top. That was what we were arguing. So I want to see all 3 because I want you guys to see the distinction between them. There is a distinction. Where's your third one? Yeah, let's say we flip this guy over. We rotate him this way, and it ends up being, I know it's the same. We're getting the same thing. That's what I'm trying to figure out right here. So one of these, one sets it is wrong because these are not exactly the same thing. So if we get this guy right here, we flip this guy. So then that means the bromine should be on top and the hydrogen on bottom. They're not the same, right? Okay, and that's this model here, right? Okay, that's it.
We're only looking at the bromide and hydrogen, right? We're not looking
Yeah.
at the-
Not at the, because they're the same, right? So that's not gonna,
yeah, they're-
yeah, so even if I flip this, like if this guy's flipped, right? That means that the bromine would be here. And then the other bromine would be here. For these two. So yeah, this should be the correct set. What was that? Okay, so it's meso. These guys are the enantiomer. So we have a pair of enantiomers and a meso. Okay, so then how would we name it? This guy would be called. What was it? So it's trans, but both of these are trans. So they haven't distinguished. Who has priority? So 1. Let's go right on the board. I mean, right on the screen. Sorry, I wasn't talking to you guys. I'm not fair. So this guy is called. Let's see. I know. I'm working on it. I'm working on it. So the first one is called cis 2,3. Dibromo butane. Don't it make you guys real happy when you guys can see the chemicals on the back of bottles and you're like, I know what that is. I can even draw that. Okay, so that's number 1. So number 2, we know it's trans. So we got the trans part down. Trans 2,3. Dibromo butane. Okay, so, but I need to distinguish between the enantiomers. How do I distinguish between the enantiomers? We're going to be using SNR. So that's 1. This is 2. This is 3. I guess no, that's 2. This is 3. 3. The H is 4. And this is 1. This is 2. And this is 3. So we have one going in this direction. This guy would be this guy, this first one. I mean, the second one.
Like it can look like an S, but then moving the H towards you.
Mhm.
I don't-
So then that one we switch the letters, right? But this kind of helps us here. That's the reason why I said let's start here. So if we have 1, 2, 3, 4, so then that would be what? So that would be S, right? Counterclockwise, right? So this guy would be an S. So then by default, this guy's going to be an R, right? So the reason why is because if you go like this guy goes 1, 2, 3, right? So he goes down here, and then the 4 is over here. So remember, let me go to the slide that shows that. Give me 1 second. Let me find that slide.
I didn't know the H dash over by the Fisher.
By the Fisher projection, you don't, and that's part of the default of the Fisher projection, right? But usually you have it so that you orient it so your H is going in the back. So if you notice, most cases they have their H's going into the back unless you have something that's being trans to each other. Does that make sense? So I'll show you. I'll come back to that. Okay, here we go. Okay, so here we have 1, 2, then 3, right? Sorry. Okay. So if the lowest priority is on the vertical bond, okay. So in other words, lowest priority is here, right? So then in this case, there's 1, 2, and 3. So then this is your R. This guy's 1, 2, and 3. That is your S, right? And then what was the other case? There. It's the one that's complicated right here. So this is what we have right here, right? Because we have the H on one of the sides, right? So then we have 1, 2, then 3. So this guy would be considered S, right? Because this guy is R. You're 1, 2, 3. Where are you going over here?
That's because it's on the horizontal.
Yes, because it's on the horizontal. That's right. So your lowest priority is on your horizontal, then that makes your R counterclockwise in this case. So where your lowest priority is on the vertical. Are you with me? That's what organic chemistry is. It's memorizing, right? So you want a little cheat sheet of card. You have to remember that. Yeah, projection. Yeah, but even with the other ones, it's still the same concept, but then you're just going to orient it because it's still going to be exactly the same, right? Do you understand? Because it's going to look the same either way, whether it's the Fisher projection or if it's the other, just a standard wedge dash. Still going to be the same problem. Come on. Okay, does that help? Sort of. You're like, I was going to, that typically means sort of, right? This one, cis, because the bromines are on the same side. Yeah, the methyl groups. Yeah. Oh, here? Yeah, these are all screwed up. Yeah, these are all screwed up. So let me put an X through that. Wrong. Those are all wrong. Okay, that's what I was saying. The bottom one is the correct one. I need to email them about that figure. Okay, sure. Okay. Erase. Okay, so let's do this guy we don't have to worry about. Okay, let's do this guy. The bromide would be 1. Okay. The CH3 or with the other carbon, long carbon chain. 1, 2. Okay, so that would be 2. Then it would be this guy. This guy was S. Okay. And so then this guy is, yeah, because they're going to be opposites of each other, right? That's the whole thing about it being enantiomers. One of the benefits. So if this guy is S, this first one is an S, then this has to be an R. So then what is this guy? You said R? Not necessarily. Yeah, they both could be S's, right? So that's 1. This is 2. This is 3. Or no, sorry, that's 1. This is 2. This is 3. And this is 4. So these guys are up there. Are you sure? Let me use a different color because then that might help it. Okay. Okay, so okay, this is 1. The bromine is 1 down here. Okay, now that is supposed to be purple. Does that look purple to you? Oh, sorry. This is 2 here. This is 3. And this is 4.
Start going clockwise, and then just because H is on the.
Okay, so we start 1. So we set 1, 2, and then you say it goes opposite. So it, go ahead. Yeah, but they're both on the horizontal, right? Are they not? Just because that the lowest priority, I understand what you're trying to say, but let's take a look at this. Did I go too far? Okay. This one here, 29, you mean 28, 29. Okay, so here, so we have 1. Okay, so here we have 1, 2, 3. So that would be S. This guy is on a, so if we go, it's going clockwise, right? This guy's going clockwise. And so since this guy's going clockwise when it's on a horizontal, when the lowest priority is on a horizontal, it goes to the S, right? So if we take a look at ours, this was 1 up here. I'll have to take a look, but because my numbers are all screwed up here. No, here's 1, here's 2, here's 3. So 1, 2, 3. So that guy is going clockwise, right? So then that would be an S. So this guy would be an S down here. Then this guy up here goes, if I remember correctly. Oh, crap. I have too many letters. The number on top of the 4, that's 1, that's 2, that's 3. So that's also going clockwise, right? Clockwise. So then they're both SS. So then that means that the other side would be RR. Yep. So then we would call this guy arm would be, let me go. I guess we should probably go to the figure. Oh shit, went too far. Sorry. There we go. Okay, so this guy, the first one, number 2, is going to be S. So that's 1, 2, 3, 4. So 2, 3. So it's 2S, comma 3S dash trans 2, 3 dibromo, and then that is going to be in parentheses. Okay, so actually let me type it up. So then the other one by default is going to be, what was that? Yeah, it's going to be RR. So it's going to be parentheses 2S, 3S. Dash trans. And so this guy is going to be RR. So it's going to be 2R, 3R. Okay. Okay. Are you guys with me? Okay. So let's move forward. Yeah, on the S's and the R's. So that needs to be in parentheses. Okay. So the Meso compounds, they're optically inactive. So even though that they do have a asymmetric center. Okay. What does that mean? You guys remember what optically inactive means? This guy is optically active, meaning that they're active, they're able to be moved. So the R and the S with that plus minuses are able to sit there and be moved. Where optically inactive means that we're not able to be moved. So it's going to be all oriented the same way. Make sense? Actively inactive basically means that they're not going to be able to be moved, right? So in other words, we can't polarize them, or they're already polarized. They're in that one direction, and that's it. That's the only way that they can go. That's it. Okay. Where something that is optically active, that means it can be polarized. Okay. So, which makes sense, the R's and the S. The Meso it's neither R or S, it's just a single compound. So it's going to be optically inactive. Okay. Okay, so these guys, the Meso compound has a plane of symmetry. You guys can take a look here. So in this case, this guy actually has a clear plane of symmetry. And because it has symmetrical, then regardless of how you turn it, you're going to end up with the same molecule, right? Make sense? So here's another example. Here's another example. How are you guys doing on the other side?
Hanging by a thread.
That's good. That's all you need to be hanging by, is by a thread or a fingernail, one or the other.
Feeling thread.
Okay, so let's we'll take a we'll say 5 to 10 minute break. Okay, so let's see, where did we leave off at? Okay, so we were talking about the Meso compound. So if you guys take a look at, I got ahead of myself. Okay, so basically, again, they're going to be mirror images of each other in the case of Meso. Okay, so here they have two asymmetric centers, but they have symmetry with them, right? Asymmetric center. Two asymmetric centers. So here's our Meso compound. Here's our enantiomers. These guys are our Meso, but it's showing the same thing, just a Fisher projection. Okay. Okay, here's another example. This here is our enantiomers. This is our Meso compound. Here, again, this guy is our Meso compound. These are our enantiomers. Okay. Okay, so, and then if you pay attention, the Meso is going to be cis to each other, right? Just like we saw earlier with the bromo, right? And then here again, the Meso is going to be, God, they keep fucking this up. This guy should be cis to each other again. Okay, so the Meso is going to be cis, and then the enantiomers are going to be trans. Okay, so again, this guy screwed up at the top. I apologize. Come on. Okay, so when we go about naming, we already did an example of that. If it moves. Okay, 1, 2, 3. So this guy is counter, is that right? Okay. So S, and then this guy is 1, 2, 3, the funny one where we have the, okay. So then this guy is R. So this guy is S, this guy is R, right? So 2S, 3R. You want to count in, well, it depends. So that's what we were talking about. So if it's in the vertical plane, I'm sorry, it's in the horizontal plane, right? Then we're switching the counterclockwise and the clockwise, right? Yeah, if it's on a vertical, yeah, then R goes with clockwise and yeah. Okay, here's another example. Okay, so we have 1, 2, 3. So this is the one where we have 1 in the vertical. So then this guy is S, right? So it's going clockwise. So this guy would be S because we have the hydrogen, the lowest priority in the, that's right, horizontal plane. So then here, this guy is S, this guy is R. So then 2S, 3R. Come on. Come on. Sorry, I keep talking to my computer. It just does not want to work these days. Okay, so these guys, 2S, 3R, 2S, 2S, 3R, 2S, 3S, I mean, 2R, 3S. This guy is 2S, 3S. This guy is 2R, 3R. Okay, so these are all 4 in this case. So these guys are enantiomers of each other, right? These guys are enantiomers of each other. These guys are called what of each other? What? Diastereomers. Okay. Okay. Okay, so you guys see the difference? Look at the Fisher projections. It makes it easier. At least for me. I don't know too. So you guys can see that these guys are just mirror images of each other, enantiomers. These guys are mirror images of each other, enantiomers. These guys are not mirror images of each other. Okay? This guy is going to be, oh, what do we use that plus and minus for? I forgot to ask you that earlier. In front, there's also a plus and minus. Okay, it has to do with us being tilted and non-tilted. Okay, but it has to do with, so tilted and non-tilted. Okay, yes, it has to do with the polarization. That's right. So it had to do with how things are polarized. So if you guys remember, some R's are S's, some are pluses, some S's are, okay? So it all has to do with that polarization. Oops. Clockwise. So if it's tilting, oh, this one back here. Okay, well, so certain things will rotate clockwise and certain things will rotate counterclockwise. So that clockwise rotation means that it's a plus. If it's counterclockwise, it's a minus. Okay, but enantiomers that are S and R could be either one, right? So they could, some of them could be pluses and some of them could be minuses, right? So that just means that they're polarizing in a certain direction. Okay, so like this guy, this is an S. Both of these are S, right? But this guy is S and it polarizes in the plus direction. So it polarizes clockwise. This guy is S, so it's still, again, we take a look. That's priority is C, that's 1, that's 2, that's 3, right? So that's clockwise, right? Clockwise. Mm-hmm.
It's going, if it's on the horizontal, it's going clockwise, it goes to opposite S, and it's positive.
No, because this guy is 1, 2, 3, right? This guy's also 1, 2, 3. So both of these are S because we have X, we have the H on the horizontal, and then so it's going to be the opposite, right? So that's 1, 2, 3. So if this guy's going in the clockwise direction, it's going to be an S in this case, right? Rather than in the vertical where it's right. So both of these guys are S's, right? So that's 1, 2, 3, 1, 2, 3. They're both. We have H in the horizontal. Lowest one in priority. The lowest priority is in the horizontal. I mean, not horizontal, and the vertical. Horizontal. Okay, in the horizontal. So that means that we switch it. So then that means clockwise is S. This guy is going clockwise. This guy is going clockwise. So both of these are S's, right? Okay, so this guy polarizes to clockwise. So that means that when we do polarization, it shifted clockwise. This guy shift counterclockwise, right? And that polarization really has to do with what's on it, right? Who's attached to it and how it's behaving, right? And so that affects the polarization, whether it's going to go clockwise or whether it's going to go counterclockwise. Yeah. So talk to her about S and R and plus and minus. That's right. Yep. SR plus and minus, right? Okay. So let me take one step back. Polarization is going to be dependent on your moieties, right? Your functional groups that are hanging off that carbon. So we have our carbon here. So the way it turns, it's going to be dependent on the functional groups that it has. Okay. And then also how those functional groups are arranged with each other, right? So that's one of the ways that we can sit there and determine your S and your R's is by using the different functional groups because they're going to polarize differently. Okay. So they're saying that sorry, I don't know why it's not moving. Okay. So here, both of these are in the S orientation, right? Yeah. So this is 1. This is 2. This is 3. This is 4. This is 1. This is 2. This is 3. This is 4. Okay. So okay, both of these are S. Hold on. Back, front, 2, orientation. Towards this 1 in the plane, 2 in the plane. So 1, 2. Okay, so do me a favor. I want you guys to make this structure, right? And then I want you to hold it from hydrogen in the back. Make the first one, and then I'll explain it. Okay. So this guy is 1, this guy is 2, this guy is 3. Right. So this is now you're holding it. I think it occurs only when they're in the vertical plane. Mhm.
Yeah.
So 1, 2, 3, clockwise, right? So these are not occurring in order, right? So, but R is still clockwise in this case, right? We have 1, 2, then we go over to 3. Right? So, yeah, but in this case, hydrogen is on the horizontal, right? So this here, hydrogen's on the vertical, right? Here, hydrogen is on the horizontal, right? So then it switches it. Counterclockwise is R, clockwise is S. So this guy, so if we take a look at ours, we have our 1 at the bottom here, not at the top. So let me go back to. Okay. This guy's 1, right? So if we shift this guy, we turn it, right? So then we put this guy up top. So if we put this guy up top, then 2 is going to be here. And then 3 is going to be here. Do you understand? So then that's 1, 2, 3. Right?
So like the strongest one is on
The one that has the most priority. Right now, the one that has the most priority is the top, right? Then this guy has the second. Right.
so is the like highest priority supposed to be on the line?
Yeah, so that's idea that it's on the line. Right, so if we go back. But it's not always that way, right? It makes it easier. So line here. 1, 2, 3. So like this is the 1, that's the 2, that's the 3.
So the like strongest, like the highest priorities are supposed to have the line, and then the third one is supposed to have the one pointing outward, and then the dash is the
So ideally, this is the best way. Where we have 1, 2, 3. Easiest one to read, right? That's the easiest way. But in reality, we're going to have all possibilities, and so you just need to be able to adjust, right? So this is 1, 2, 3. So that one would be S counterclockwise, right? This guy is 1, 2, 3. That would be clockwise. Both situations, you have H in the back, right? So if we have H in the back, but right, then we have my right here. We have the what? The highest. So we have the highest priority, right? So you're saying we're shifting this so that our highest priority is here, right? Then that means that the other one, the number 2, would be here, right? So this is that, right? So we have carboxyl, we have the OH, the alcohol, and then we have the methane, right? So right here, three-dimensional structure, this guy, reorienting them. Right? What was that? Number 33. So, right? So this is what the positive and negative means, right? It's just how it rotates, how they rotate. Does that make sense?
But you can't actually like do that part of it like all of it.
Yeah, I would have to give you a polarization picture to let you know whether or not it's positive or negative. Right? So that would be the only way you can tell.
So what do we look at? Do we look at that last part?
Yeah. So if it rotates in a positive direction, so let's see, clockwise direction, right? So clockwise direction, then it's positive. If it rotates in a counterclockwise direction, then it's negative. Okay. So that positive and negative only refers to polarization. Make sense? Okay, so enantiomers, SNR enantiomers, could be mixtures of both. They can be a positive and a negative. But we know that enantiomers are going to be opposites of each other. Right? That's right. So, yeah, if you have, so that's what they're saying. Some enantiomers are positive, some of them are negative, right? Some R enantiomers are positive, some of them are negative. And so that means that the S is going to be the opposite of that. So. Okay. So this here is an example. So here, this enantiomer, right? This one is positive, right? So this enantiomer is negative. You guys, you have that look? You have that look? It just look like, I'm not quite sure exactly what you just said. So I just said that enantiomers can be, R enantiomers can be positive or negative. S enantiomers can be positive or negative. If your R enantiomer is negative, then your S enantiomer must be positive. Get that? That's right. Yeah. Yeah. So does that help? Yeah. Okay. Practice. Yeah. Okay. I'll give you guys more practice problems. You don't need, you want more? It wasn't enough, right? Yes. I will. I'll extend it, yeah.
Why is it like based? It seems like it's based on like the formula we went over. I think.
You want me to give you more?
No, like
Homework.
class, so then we know.
Yeah, I gave you guys, I did the one problem. Actually, we did two problems with the formula. Remember, we did two problems with the formula. Yeah. Yeah, so that one I'll give to you because we didn't go over enough examples of that. But you're talking about the formula with the thing, yes, the absolute problem with this one here, right? Yeah, based upon this family. Okay. I'll start adding a little bit more questions to my lecture. So I'm working on. It's a process. And the question that I did add was taken out. It wasn't in the notes. It was actually because we did do two problems. One we talked about where we calculated the angle or the sounds good. Well, that's after we finish this. Let's get through this first. I have a plan. I have to stick with my plan to some extent. Yeah. Okay, but what I'll do is like for your on Wednesday, you guys have your lab. So we'll spend 10 minutes, 10, 15 minutes doing problems. How about that? Okay. Okay. Okay, so the last thing is that the physical properties, right? So if you guys take a look at it, so these here, so this here is the Meso compound. This here is the enantiomers. Okay, so if we take a look at the Meso compounds compared to the enantiomer, the Meso compound to the enantiomer, the Meso compounds, they have the same melting temperature. They have their specific rotations are going to be opposites of each other, that plus and that minus, right? And you notice that they put their plus and minus here because they were able to calculate it using polarity, right? And then they have the solubility. Now these guys, the solubilities are going to be exactly the same in this case. Now the Meso compound has a different melting point, right? And it doesn't rotate because it's inactive, optically inactive. And its solubility is 125. Now, if we take a look at the plus and minus, so that in other words, we're having this, and we have some of this, right? So if we take a look at this, its melting point goes up, right? Its specific rotation, well, these guys are going to be canceling each other out. But its solubility it's finally starts to solubilize at 139, where this one solubilizes at a lower concentration. Right? So you'll get this guy. So for it to be completely soluble, you have to at least go to the 139. Does that make sense? Okay. So this is the interesting part right here, right? That melting temperature. So that suggests a couple of things, particularly since we're working with a product that has a lot of hydrogen bonds, right? So you have a lot more hydrogen bonding occurring between the two different compounds by their orientation. So the accessibility plays a part in that. So that's also increasing our melting temperature, our melting point. Make sense? Okay. So how, well, now that I've talked about it already, how would you describe the difference in this? I mean, based upon what you guys see, other than what I just told you, in your own words. Should have been the question I asked before I gave you the answer. So why is there a difference between, let's say, this guy, which is a combination of all of them together, right, versus each pure form? Why does this guy have a higher melting point than? Well, what do you mean by it has more stuff added to it? So quantity-wise, so we could have the same quantity, it still would have the same melting. The intermolecular forces, but don't they have the same intermolecular forces? Because aren't they the same? They're the same chemical formula. Sterically, they're the same except mirror images of each other or where they're located. What was that? Yes, but why? Okay, and so these guys are acting opposites of each other. That's what you're suggesting. And so then I can get more hydrogen bonding occurring between these two and then these two, right? And then on the other side, I could have hydrogen bonding occurring over here as well, right? So because you have a mixture of both moieties, it allows, because these guys are going to be cis to each other, these guys are going to be trans to each other. Okay. So because of that, then if these guys are cis to each other, we're going to get hydrogen bonding occurring between the two water molecules. We're also going to have good hydrogen bonding occurring between the hydrogen and water. And then on the other side, you're going to have another set of hydrogen bonding here with, let's say we have one or the other of these, right? So it's going to be a lot more sticky because where things are located at. Where these guys, you have this hydrogen bond that is occurring, where you're not going to see it between these two. Right? And then if you have these two mixed together, or if you have this guy and this guy, then you're going to have hydrogen bond here and here, and that's it. Where this guy has 3 points of hydrogen bonds, this guy has 2 points of hydrogen bonds. Does that make sense? So making it a lot more sticky. So you're right. The intermolecular forces, the fact that you're able to form more and more hydrogen bonds based upon the orientation, the way it's oriented. Does that make sense? So you guys kind of looked at me. Yes, they're also going to be affected as well too, because depending on what's available, it does change those as well too. Because they're inducible, right? So those are inducible forces. Does that make sense? Or not? Don't just nod to nod. Okay, so we could also have asymmetric centers with nitrogen and phosphorus. Okay, and here's examples of that. Okay. Come on. And this shows you, this is an amine. Oh, I got carried away. Okay, so this is an amine inversion. Okay, so here's 1, 2, 3. This guy is going to be sp3. This guy here, sp2. So then we get the formation of the sp3. Okay, so these guys would be enantiomers of each other. So one going in one direction, the up direction, one going in minus direction, and then we invert our 1, 2, 3. Or keep our 1, 2, 3. Okay. Okay, so these enantiomers, they can't be separated. Okay, so when we talk about receptors in terms of protein receptors, so these guys are kind of relying on these structures, right? So we can have a receptor that is chiral, it's able to bind to one of the enantiomers, but is not able to bind to the other enantiomer. Okay, so here's an example. So this guy will bind to R, so you get binding occurring at all 3 points. Here, we don't get all 3 points binding. Okay. Because over here is a circle, right? This represents the binding site of the receptor. Over here is a circle. This one is a triangle. This one is a square. If we have the S enantiomer, we switch this. It won't be able to bind. Okay. So, and receptors use this quite a bit, you know, in terms of selectivity. So you'll have receptors that the substrates are very, very similar, but the only thing one is an S and one is an R. Okay. We also use this in the case of sugar, sugar that we process. We process L. Yeah, I think we process L. We don't process D. L and D are the same equivalent of S and R. We'll talk about it when we get to the biochem second semester. Here's an example of two enantiomers. So this is the R minus carbon. This guy smells like peppermint. Okay. This is the S plus carbon. This guy smells like caraway seeds. So one is kind of stinky, one smells minty fresh. Okay. And you'll notice their properties are the same, right? The only thing they're enantiomers of each other. Different receptors, that's right. Okay, so so meth and the ingredients that is in the Vicks vapor inhaler, right? So these guys are enantiomers of each other. This is meth. This is what the ingredient in the Vicks vapor inhaler, right? I probably shouldn't say that because I wonder how many people now are going to go out and buy Vicks vapor inhalers and then make it into meth. So, okay, so these guys have different physiological properties. One will rot your teeth. One will actually allow you to be decongested. One will keep you up all night. One will help you sleep, you know, so. Okay, so the way that we separate enantiomers. So we talked about the concept of the polarization. That's one way of doing it. The other way of it is separating by hand. So we could basically use a separating chromatography. So because we know that we can polarize the moiety, we can use that polarization to sit there and run them and separate them on a column. Okay, so we'd have to go through the process of polarizing them. One is going to be left-handed, one is going to be right-handed, and then allow for the column that we're using to separate the two out. And so basically this is what you're going to end up getting. So you're going to get the separation of them slightly different from each other. As a result of the polarization, one's able to fit through the thing and one isn't, or fit through it in a certain systematic way than compared to the other one. I feel like there's something missing in my tree here. It is. So there's a column, I mean a test tube down here. So this is just a column. You can't see everything. There's a funnel. You guys can see it on the notes, right? I don't know what's going on with the images here. They're just not showing everything. So that's it. Piece of cake. Yeah. So chapter 5. Okay. So we've talked about stereochemistry. How are you guys feeling on it? Piece of cake? It is. Okay, so our next chapter is we're going to be talking about alkene. We've already talked about alkanes, so now we're going to hit some alkenes. Okay. So, yeah. Okay, so alkanes, different from alkenes, is that alkenes have at least one double bond. Okay, so they're hydrocarbons that have at least one double bond in that structure. So for instance, this guy is an alkane, all single bonds. This guy is an alkene. Alkaline, yes. Alkane, alkyne with a triple bond, yes. Yeah. Okay, so when we talk about the degree of saturation, the degree of saturation is just going to equal the number of pi bonds and rings. Okay, so in the case of an alkane, which is totally saturated, right? You can basically use CnH2n minus 2. Okay, so if we're talking about methane, methane is C is 1, right? Or I'm sorry, N is 1. So you have C1. And then if N is 1, then actually this is wrong. It should be plus, yes. Yeah. Oh, it is a plus. Yeah. Okay, it's just not showing up very well. So it's plus 2, right? Not minus 2. Okay, so, and that's the case of an alkane. Okay, so then that's, so if it's 1, so then that's a total of 4. So it's CH4, right? If it's octane, then C is 8. So C8. And then we have H16 plus 2, 18. Okay, so when we talk about now we're talking about a single alkane, it's going to be CN2N. Okay, so if we're talking about octene, where there's only a single double bond, then we're going to have C8, H16. Piece of cake? Okay, so ring structures also are going to have the CH2N. Okay, so cyclic alkenes are going to have CnH2n minus 2. Okay, so if we have cyclooctane, so then that guy is going to be C8H16. Okay, if we have cyclooctene, so then that guy is going to be C8H14. Okay. Okay, so then so you're going to get minus 2 hydrogens for every pi bond or ring structure. So you're going to lose 2 hydrogens for every pi bond or ring structure. So if I have 2, let's say I have a diene, that's going to increase my pi bonds, right? So that's also going to give me another minus 2 added onto it. Or if I have a triene, that's right. Does that make sense? Does it make sense? Okay, so let's do, if we do octadiene. Okay, what does that mean? Di meaning 2, right? So 2 double bonds. Okay, so if we draw that out, that's 1, 1, 2. We can put them anywhere. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So I can put a double bond here and a double bond here. Okay, don't matter where it's at. Okay, so this guy has 3 hydrogens right here. So I'm going to write 3 next to it. in a different color. How about green? So there's 3 here. This guy has 1 hydrogen. This guy has 1 hydrogen off of it. This guy has 2 hydrogens. This guy has 1 hydrogen. This guy has 1 hydrogen. This guy has 2 hydrogens. This guy has 3 hydrogens. Okay, so we add all together. That's 6, 7, 8, 9, 10, 12, 14. Okay, 14 H's. Okay, so we said it's C8, H14. Because it's a di, it loses 2 hydrogens for every pi bond, which means double bond, right? Double or triple bond. Okay, so we have an additional double bond. So then that's how we end up with that 14. Make sense? Okay, so if we calculate the total number of pi bonds, 1, 2 pi bonds here, right? So our degree of saturation is going to be the total number of pi bonds. We have 2 pi bonds, 1, 2. So the degree of saturation will be 2 in this case. In a ring structure, if we had a ring, we'd have 1 pi bond because there's only 1 ring. You guys get it? Cameron? What was that? Okay, let's see how well you guys think about it now. In real context, for real now. Okay? Maybe. There we go. So what is the degree of unsaturation of a compound with a molecular formula C23H38? The degree of unsaturation. So again, saturated means that there's no double bonds or triple bonds. They're all single bonds. Unsaturated means that there are double bonds. How many double bonds does this guy have? Basically, because every double bond represents a pi bond and a sigma bond. Pi bond and sigma bond. Pi bond and sigma bond. Okay. You said 0? Okay, so let's do it if we were all single bonds. How many, if we have 23 carbons, how many hydrogens should I have? All single bonds. So it'd be CN plus, and H2N plus 2, right? Isn't that the equation? Okay, so if you said if there's 23, then we should have 2 times 23 is 46, so 48. Is that true? Should check my math because it's been a long day. You got 8. Okay. You got 4? Okay. So we have 8 and 4. Anybody else got anything else? Because we have 38. Right? So remember, it says you lose 2 hydrogens for every double bond you have, right? Okay. So if we lose 1, so that's 1 double bond, right? So then that would be, so we need to lose how many? We need to lose a total of how many right here to make it 38? We need to lose 10. right? Because 48 minus 38 is 10. We divide that by 2. Okay, so this is if it was all saturated. So if we have only single bonds, right? This is what it would be. This is the equation, right? So we calculated C23, H48, right? So the only thing that we're changing are the hydrogens, right? Because either we're getting rid of them or we're adding them, right? We can't add any more than what we have when it's saturated. So that means we're getting rid of them, right? So if I'm going from 48 to 38, how many am I losing? 10. So 10. And they said if we lose for every double bond or ring structure, we lose 2 hydrogens, minus 2, right? So 10 divided by 2, 5. So that's how we calculate our degrees of saturation, because it's the number of pi bonds that we would have, or the number of double bonds you would have, because every double bond has 1 pi bond. There's a pi bond and a sigma bond. You guys have to remember that, right? We talked about that at the beginning of the semester. You guys all threw it out the window, didn't you? You're like, remember what? Never going to talk about that again, right? You get that? Okay. Good. Okay. It's easier if you do it from the saturated formula, because then that kind of makes it a little bit easier. If we let's say if we're talking about a triple bond, right? Triple bond is going to be 2 pi bonds, right? So there's going to be at least 2 pi bonds in that situation, right? And a sigma bond. So 2 pi bonds and a sigma bond, that makes up a triple bond. Okay, so then that's going to be a little bit different, right? And so, but if you start off with how much is saturated, then you can figure out how much you're losing, because in the case of a triple bond, so let's say a triple bond looks like this, right? Let's try it out. So C, 1, 2, 3, C, and then it has these guys hanging out on the sides. So if these guys are hanging out on the sides, then it's going to either be an H or it's going to be another carbon, right? So if it's another carbon, then you don't have anything hanging off of here, right? Because of a triple bond. So that's why I said it's a lot easier if you start off with what we're saturated with. Yeah, that's right. Or you can be hardcore and just draw it, right? Old school, old school. Exactly. Take you half the exam time to sit there. Okay, so come on. So now we have alkanes, which we know are saturated. So there are no double bonds. They're all single bonds. Alkenes have at least 1 double bond. Okay, E and E, 1 double bond. Okay, so we have at least 1. And so that makes it unsaturated, right? Makes sense. Saturated, it's saturated with hydrogen. Unsaturated, not saturated. Okay. Okay, so what is the formula for a 5-carbon hydrocarbon with 1 pi bond and 1 ring? C what? C2? A 5-carbon hydrocarbon. So then C what? So 5. And that's if it's saturated, right? Okay. So then we lose how many for a pi? So -4. So it's C5, H8. Okay. That is correct. Oop. Which works out the same way because you're losing 2 this way and you're losing 2 this way, right? So you're losing a total of 4. It should always work out that way. So that's, you're losing 2 for the ring structure and you're losing 2 for the double bond, right? So yes, ma'am. Yes, Ed. Because the 12 is, it's 2n plus 2, right? So that's what it would be if they were all single bonds. Okay, so n being 5, right? Because there's 5 carbons. So 5 times 2 is 10. Yep, plus 2 is 12. Okay, so then we know that we lose 2 for every pi bond we have, and we lose 2 for every ring structure we have. So -4. Okay. Okay, piece of cake. Okay, I'm gonna try to push the time a little bit. Naming is real simple. You replace A and E with E and E if there's a double bond. Okay, and then you just got to tell me. Oops, I got carried away. You got to tell me where the E and E is at. Okay, and we always want to count it so that the functional group gets the lowest possible number. We always want to try to give it so the functional group has the lowest possible number. Okay, again, I'll say functional group has to get the lowest possible number. You always want to count the longest chain. So that's 1, 2, 3, 4. So we start from over here because double bond is right here. It's the functional group that we're talking about. It has the lowest possible number. So the double bond is always between that first carbon that it starts on to the carbon that it ends on. So it starts on the 1, so you just use the 1 to give it its number. Okay, this guy, 1, 2, 3, 4. So this guy would be 2-butene. This guy, 1, 2, 3, 4, 5, 6. So this guy would be 2-hexene. Okay, this guy, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Ooh, this is a good one. I'm gonna count that wrong. 1, 2, 3, 4, 5, 6, 7, 8. I did count it wrong. Okay, so here, the longest chain is an octane. However, the functional group is a double bond. So they give the double bond the priority because they want it to be part of the main chain. It makes it easier to name. Okay, so I'm going to tell you this, right? So you will see in chemistry, they don't always obey this rule, right? A lot of times they will actually make this guy a side chain. Okay, and you'll see that. And when they make it a side chain, they use E, N, Y, L. So this guy here, single carbon, they would call this guy meth. Okay, and they would make it a side chain. And then this guy would be the, okay. You will actually see both cases. One will be a synonym of the other. Okay, just so you know. But if you have the option, it's easier to do it this way. Yeah, so the YN, YL, because you remember when it was a single bond, it was just YL was added on. So here we put EN, So it would be methylenol, methylene. Okay. So when a double bond is in a side chain, you put ENYL. Okay. And you will see that, and I'll show you other examples of it. So, but I want you to know both ways. On your exam, we're going to go with what the book says, because that's what you're going to learn. Okay. So there are going to be stereochemistry that's going to exist. Now, this is kind of cool because it's going to be really limited, right? Because since it's a double bond, it's not going to be able to flip around the way it does with single bonds, right? You're going to have it's rigid, it's stuck, it's not going to flip, right? So if it's going to be cis, it's going to be cis, right? If it's going to be trans, it's going to be trans, okay? So here, you guys can see cis, trans, cis to pentene, trans to pentane, or we can use our Z. Z, E. E means apart, right? Z means together. Okay. Piece of cake? Okay, I know. We're almost there. I know. I got 2 minutes, right? Something like that. Come on. A minute. Okay, real quick. So if I have 2 double bonds, I use diene, right? If I have 3 double bonds, I use triene. If I have 4 double bonds, I use tetraene, right? Piece of cake? Okay, and so you guys can see here, right? That's right, and you have to give the location, right? So this guy is 2, 4. So it starts at the 2 carbon, it starts at the 4 carbon. You guys see that? This guy is 1, 3. Starts at the 1 carbon, starts at the 3 carbon. Okay. This guy is 1, 3, 5 hexatriene. Starts at the 1, the 3, and the 5. Piece of cake? So far. Don't worry about it, we'll make it harder. Okay, so we're going to stop here.